AC circuit theory, AC circuit components, or RLC circuits. When looking at these components, we're going to look at the resistor, the inductor, and the capacitor, and the effect that they have on voltage and current when applied to alternating voltage and alternating current supplies. We're going to look at these components as pure components. First component is the resistor. When a resistor is connected into a circuit with an alternating supply, we know that when current flows through the circuit and current flows through the resistor, we will develop a voltage across that resistor. As a pure component, that voltage is represented on the horizontal axis, and the current is also represented on the horizontal axis. And whether it is series or parallel has no bearing on the component. Simple Ohm's law applies. IR equals VR over R. The size of the current flow through the resistor depends on the voltage across the resistor and the resistance of the resistor. We need to remember that our Phasor diagram is a representation of what happens as it rotates, and we will see that as my voltage shows my sine wave, my current flow will also show a sine wave. We must remember that because the voltage and the current are two different entities, two different units of measurement are used, so scale is not relevant when it comes to the resistor. For series and parallel, the resistor responds exactly the same. Inductors. The inductor is a reactive component, which means it develops a reactance or an apparent resistance. The ideal inductor has no internal resistance, and as a result we can accept that it will allow infinite current to flow. However, when we supply the inductor with a voltage or a current, when we supply a current through the inductor, what happens is it generates a magnetic field. And we know that magnetic fields lines can't cross. As a result, as that magnetic field expands, the surrounding magnetic fields push against those magnetic fields, and that stops the expanding of the magnetic field, which in turn limits the amount of current to flow. Because of that, my inductor will generate a voltage, and the effect of that voltage is, or the effect of that voltage and that current is that there is a delay in the current flow that is generated or allowed through the inductor. When looking at the effect of the frequency, the inductive reactance is equal to 2 pi f, which is the angular velocity, times the inductance. The result is, at a range of frequencies, my reactance, which is measured in ohms, will increase as my frequency increases. Looking at the Phasor diagram and the impedance, or the ohmic reactance diagram, we see the following. When I supply in series, when I pass a current through in series, it will develop a voltage which has a 90-degree lead with reference to the current. In series circuits, my current is the reference, it's the same through all the components, and the voltage divides up over the three components. That's why my current is the reference. As it's a pure inductor, that phase shift there is 90 degrees. When it comes to parallel, we get the same, but my voltage becomes my reference. The voltage across all the parallel branches are the same, and as a result the currents are going to divide. So the current flow, or the voltage, becomes the reference, and my current flow will lag by 90 degrees. Again, this is a rotating vector diagram. The capacitor has an infinite resistance due to the dielectric in the middle, but when we supply voltage to the capacitor, current flow is at a maximum. As that voltage increases, the current will decrease. So as a result, the inductor also develops a reactance. Ohm's law also applies to the capacitor, but the reactance Xc is equal to 1 over 2 pi Fc. That will result in the ohmic value decreasing non-linear with reference to an increase in frequency. So as current flows in, it's at maximum, and then it will charge a voltage across the capacitor which will increase as the current flow decreases. So in series and parallel, the capacitor will have the current as the reference on the horizontal axis, and it will have a lag in the voltage across the capacitor. In parallel circuits, the voltage becomes the reference, and then the current will lead the voltage by 90 degrees. Again, these are rotating aspects which needs to be indicated in all diagrams. As with the resistor, current flow is going to equal the voltage on the resistor divided by the resistance. The current flow in the inductor is equal to the inductive voltage divided by the inductive reactance, and then the capacitive current is equal to the voltage on the capacitor divided by the capacitive reactance.